had to be 6 feet.
So I've got sort of an outline of what we're talking about up here. Basic givens in science, an example of how we get lost maybe a little bit. Talk about, is there life out there if we have time to get to that. So first, just a reminder of what we talked about last time. I'll throw up the picture. We talked about that model, the Big Bang model of the universe, where you have weird things like space-time expanding and mass embedded in that space-time, and everything's flying away from everything else. Anyone come up with any questions since that time that I talked about it? I know some of you had lots of questions, but we're maybe not wanting to ask them. Anybody have any questions about any of that? It's okay, no questions, stupid. You don't have to be intimidated by it.
Is that word way to the right warp?
No, that word is WMAP. That's the name of the satellite that took
I
some
didn't
of the
see all the
data.
letters from
Yeah.
So wait a minute, we got Star Trek up there?
I needed, yeah, warp time here. All right, so let's move on to what I was going to talk about today, which is the basic givens in science, things that most scientists would agree with about what they do, the things that they take to be given about what they do. And this list that I have up here, it was adapted from this book called Origins by the Harzmas at Calvin College. Lauren Harzma and Debbie Harzma together wrote this book called Origins. And they talk about some of this Big Bang stuff in that book, and they compare and contrast agnostic or even atheistic scientific worldview and a Christian worldview in that book. It's a good book to take a look at. But in any case, basic givens in science. Human reason works. Can't really argue with that. We can call it human wisdom. We could call it logic, deduction. Any of those things, any of those capabilities that we were given by God, they work to help us understand the creation. Science people wouldn't necessarily use all the words about God giving us these gifts and God making this creation. But they would agree that, yeah, my reason and my ability to deduce and my ability to use logic, my ability to use math, that all works, and it works well. A second thing is that natural phenomena can be modeled using that reason that we have. We can use that reason, we can observe very carefully the world around us with our senses, and we can make models about what we observe. And our models progressively get better. So you drop a ball, it falls to the ground, that's a model. Every time I drop something, it's going to fall. It's not a very predictive model, it's not a very useful model from a scientific standpoint, but it's still a model. And we can build better and better models. We could start building models that predict how long the ball is going to be in the air before it hits the ground. We can make models that predict how fast it's going to be moving before it hits the ground, that sort of thing. The next thing that's very important is that natural phenomena are repeatable. So each time I drop the ball, it's going to fall in the same way, or roughly the same way. And that's important because the last thing that people in science agree with about what they come into the whole scientific endeavor with is that these models that we make of natural phenomena have to be testable. In order to be able to test something, you have to be able to repeat it a bunch of times to make sure that your model is working. So all of these are things that science people come into a problem with. And as a Christian, none of those, we can't really have a problem with any one of those. And you understand it from a slightly different perspective than a person who maybe is an agnostic or an atheist and coming into science. So those are the givens. That's what science people think as they go into their study. But we tend to sometimes get lost, and these are the places where we start to get lost anyway. we start to really believe our models. We start to believe in our models. And we start to think maybe that there's no other reality than what we observe with our senses. In fact, the only reality out there is the one that we see with our senses. And the other way that we get lost is that we start to believe that the model is the reality. There's nothing more real than the model. So even though it's a model, you build a model of a car when you're a kid, you glue the model together and maybe it rolls, but it's still just a model, and you know that. Science people sometimes forget that what they're building is a model, and they start to think that that model is it. In fact, I have colleagues at work that are so tied to their models that their whole career and their whole self-worth hinges on the model that they develop or help to develop be true and continue to work. And if it stops working, things fall apart for them, things start unraveling for them. So people can get really attached in the scientific community to their models. You can get involved in some pretty heated arguments with people over models. It's just a model, guys, come on. So things that kind of keep me grounded, the passages that kind of keep me grounded, and I have them on my phone. I'm trying to get better about remembering verses. But Romans 1, verse 19 through 20. Let me just read that to you. Find it here. Maybe someone can recite it for me right off the bat, because they're better at this than I am.
I can read it for you, Geoff.
Sure, go ahead.
The Romans 1 passage.
Yeah, the Romans 1 passage.
Since what may be known about God is plain to them, because God has made it plain to them. So that's actually a phrase following from verse 18. For since the creation of the world, God's invisible qualities, his eternal power and divine nature, have been clearly seen, being understood from what has been made, so that people are without excuse.
So the key words in that passage are God's invisible qualities. It just reminds me that there's more to the reality around us than what we can observe with our senses or our best meters or whatever. There's more to it. 2 Corinthians 4:18 talks about the same sort of thing. I'll bring that one up. And we look not to the things that are seen, but to the things that are unseen. For the things that are seen are transient, but the things that are unseen are eternal. Again, just reminding me that what I see and what I model is not the true reality. There's an underlying reality there. Hebrews 11, verse 3 talks about that. Romans 8:22 also talks about that as well. These are some passages that keep me grounded and are able to help me sort of detach from the models that I look at as a scientist and recognize that it is just a model. And if it doesn't work, it's okay. We can go back and make some more observations and try to make a better model. So what I wanted to do with the givens in science and this idea of where we get lost, I wanted to go through sort of a story, an example story of how this happened over the course of human history. And it's about the solar system. If you remember, Galileo and the church had a argument about this, and it was bad press for the church, and maybe it was a little bit of bad press for science, but that's kind of hushed by the scientific community. They still uphold Galileo as a great example of science. But back in the day when people were first thinking about the solar system and the universe, these were the things that they came into the problem with. The heavens are perfect. The heavens are perfect. The heavens are immutable. The circle is a perfect shape. And all heavenly motions must be circular, because the heavens are perfect and the circle is a perfect shape. And this is an example of all scientists, even scientists today. No matter what they tell you, when they come into a scientific problem, they're coming into it with a particular worldview. You just can't get away from your own perspective on things. It's always there. Maybe some science people are not aware of their worldviews, but they're there, and they haven't identified them necessarily yet. So this was sort of the worldview of scientists of the day, and the day that I'm talking about is around 0 AD or so, maybe hundreds after 0 AD. These were the ideas that were in play, the worldview that was in play, that things are perfect. And you know, from a scientific standpoint, you know, we say these models that we have to be testable. You know, this perfection that this worldview is talking about. I don't have a perfectometer. Does anyone else have a perfectometer? It'd be nice maybe, but we don't have meters to measure perfection. So that's a problem with this in terms of this purely scientific model of things. You can't make a model of perfection. You just can't. You know, we as Christians know that the heavens aren't perfect because of the fall. All of creation was infected by the fall, and so that's a problem right there. But anyway, these were the ideas that were in play when Ptolemy came up with his idea for the model of the solar system. And on the side there, maybe it's hard to read, red on black. Maybe a different color should have been chosen. But he said that he sort of has the first statement of Occam's razor here, that if you've got a couple of different explanations for some phenomena, the simplest one is probably going to be the best explanation. So he proposed a model for the solar system that made sense of the planetary motions. So back in his day, when the astronomers looked up at the sky, they saw that everything rose in the east and set in the west. And there are a couple of stars out there that they call planets, and that's from a Greek word that meant wanderer, because these things, they kind of wandered relative to the background stars. They moved through the background stars, and sometimes they moved funny. They would go the same direction as the stars, but then at other times they would seem to move backwards relative to the stars, and that was a problem for people. And so Ptolemy wanted to make a model of this, and this is his proposed model. He put the Earth at the center of the solar system, and he had the planets traverse circles, because the circle is a perfect shape and the planets are in the heavens. And he also had the planets traverse circles on the circles. They're called epicycles. And this explained not only the motion of the planets relative to the background stars. So you got this planet that's orbiting Earth, so to speak, and you got the stars that are outside it. And so if you look in this particular direction, you'll see a certain set of stars behind the planet. And then as the planet moves along the orbit, maybe it's over here, when you look in that direction towards the planet, you see a different set of stars over here. So it explained the motion of the general motion of the planets relative to the background stars. And it also explained their sometimes moving backwards, because as you're going around on this circle here, as the planet's moving along this part of the epicycle, it's going in the wrong direction relative to the background stars. It looks like it goes backwards for a little bit. And he built a model that fit very well with the observations of the solar system. In fact, this model was used all the way up until the time of Galileo in the 1500s. And it was a hard model to do away with, because it did so well in predicting the positions of the planets. It did a very good job of predicting the positions of the planets, and that's one key thing about scientific models. They got to be testable, and this model was tested and tried and true. It did a good job of making predictions. And it kept getting refined by people as they found predictions not matching up with observations. So not only was it a good model for making predictions, but it was a refinable model. You could make it better as time went on, and as you got better observations. So that was a model for a long, long time. And again, this model was proposed because of these ideas that were functioning in the background, that the heavens have to be perfect, that things have to move in circles, all of that was buried in this model, even if you don't recognize that. It's interesting that, I should go back to this model again, that there was another model out there at this time. Nobody really talks about much, but it was a model proposed by Aristarchus of Samos. He put the Earth not at the center, he put the Earth in orbit around the sun. He proposed a heliocentric model of the solar system, with the sun at the center and the planets orbiting the sun. He also proposed that the Earth was round and not flat, but I don't know exactly what happened at the time. Maybe he wasn't as popular of a guy as Aristotle. Aristotle's model was the one that won out for flat Earth and Earth at the center of the universe.
Where's the sun in this model?
The sun, depending on what planet we're talking about, if we're talking about Mercury and Venus, it was recognized that the sun was outside the orbits of those planets, but inside the orbit of Mars, Jupiter, and so forth. So, yeah, depending on which planet it's either outside the orbit or inside the orbit.
So Geoff, you're saying, I mean, this image, we're imagining a sphere, but you're saying they're not thinking sphere. They're not thinking the Earth is a sphere?
Right, they're thinking it as a flat disk.
Okay.
So we got this sphere here in the picture, but yeah, they're thinking Earth is flat, and so this is just a point in space from their perspective. From our location, this is what we see.
And the Western Hemisphere didn't exist.
That's right. Yep. There was only Europe and the Far East. Yep. Yeah, so this was the model of the time. There was the heliocentric model out there, but this was the one that was used because it did well for predicting where planets were going to be. Finally, in around 1500, Copernicus came along. He was a Catholic priest, and he was looking at the data, and he was starting to recognize that Ptolemy's model had to be further and further and further and further refined. It was doing a worse and worse job of predicting locations of planets as time went on. And he knew of this heliocentric model, and he found that a lot of the problems with Ptolemy's model were dismissed with a heliocentric version of the solar system. But he was a Catholic priest, and at the time, the church kind of ruled with a little bit of an iron fist, and he was very worried about publishing this model because at the time, the church was a proponent of a Earth-centered model, and he didn't want to get into trouble with the church. And so he waited until he was on his deathbed to publish the model of the heliocentric solar system. But these were his words about the Ptolemaic model. It seemed neither sufficiently absolute or sufficiently pleasing to the mind. So again, there's this pleasing to the mind thing that's buried in all scientists. You know, I want my model to be pleasing to my eye, pleasing in some way. It has to give me some kind of pleasure. And that's why Copernicus wanted to move part of the reason why Copernicus wanted to move to this heliocentric model, which is here's that picture. Puts the sun at the center. Orbit of Mercury and Venus are inside the orbit of Earth, and the other planets orbit outside the Earth. The only problem with this model is it didn't do as good of a job of predicting where the planets were going to be as the Ptolemaic model. It just seems simpler to explain some of the other observations, which I'm going to get to in a minute here. So that was the Copernican model. And when that came out, the church, you can't see the top of that line there, but the church had something to say about it. This was sort of the general statement of the church at the time, Cardinal Bellarmine. In 1615, said, to demonstrate that appearances are saved, assuming the sun is at the center and the earth is in the heavens, is not the same thing as to demonstrate that, in fact, the sun is in the center and the earth is in the heavens. So again, it was an argument over what's real and what's not real, what's truth and what's not truth. And we always have to be aware of and discerning that for ourselves as we read through Scripture, what's true, what's not true. But again, when we come to these scientific problems, we all have this worldview that we impose on what we see and observe. So I'm just kind of going through a list of people that were important for developing our current model of the solar system. Tycho Brahe was a guy that, he was not a nice man. All historical accounts agree on that, but he was one of the greatest naked-eye astronomers that the world has seen. He built this huge observatory for observing the stars that didn't even have a telescope in it. He just had thousands of students coming through there and making observations for him. And he made some pretty important discoveries in the field of astronomy. His measurements of planetary motions, in fact, modified the Copernican model of the solar system. Kepler, who I'm going to talk about next, came along and used those measurements to make a new model of a heliocentric solar system. He also observed a supernova while he was alive, Tycho Brahe did, and demonstrated that the stars are farther away than people first thought. He made a measurement, an estimate of the distance to this supernova with his measurements. And they were all naked eye measurements. There was no telescope, there were no CCDs or anything like that at the time. This was all naked eye.
Do they think that his estimate was at all accurate?
His estimate was, I don't know the answer to that. I don't know the answer to that. I can't remember what his estimate was. So Kepler worked with Brahe, and they didn't get along very well, but Kepler was able to rip the data out of Brahe's hands as Brahe was on his deathbed, and use the data to make a new model of the solar system. And just a reminder, this was still in play at the time that the heavens were perfect, they're immutable, the circle's perfect shape and all that. And Kepler's model involved ellipses, so that was a problem. Except it wasn't as much of a problem as it was when Ptolemy proposed his model and when Copernicus proposed his model. We weren't so worried about circles being perfect shapes anymore. But based on that data, he built a model of the solar system where the planets don't follow a circular path, they follow an elliptical path. And because of that, they move slower when they're far away from the sun, and they move faster when they're closer to the sun. That's what the shaded regions are trying to depict on this picture here. And the period of the orbit, the length of time it takes to get all the way around once, depends on the size of the orbit in a well-defined way. He was able to write down a mathematical model for that and then test that mathematical model. So again, all these models that we're going through here, we've got the Ptolemaic model, which was the Earth at the center. We've got the Copernican model, which was the sun at the center, but circular orbits. And now we got the Kepler model with the sun at the center and elliptical orbits. All of these models were tested by observations, and that's one key thing for scientific models. You got to be able to test them. Then Galileo came along, and he wrote a dialogue concerning two chief world systems in his time, and he was pretty blunt about what he was doing in that dialogue. He had a couple of characters in there. One character was named Simplicio, and this guy was meant to represent the church's position on the Earth-centered solar system. And Simplicio, of course, also means simple-minded. So he kind of dug his own grave, I guess. But he made some important astronomical discoveries. He was kind of the first guy to take this new development in the scientific community of lenses and put them into the shape of a telescope and look into the skies. And so all of those 4 ideas, the heavens are perfect, the circle is a perfect shape, the heavens are unchanging. Well, Tycho Brahe, because he observed that supernova, kind of knocked out that the heavens are unchanging. They are changing. We've got this new star in the sky, this supernova. But Galileo knocked out a lot of the other ones. He observed Saturn with his telescope, and he saw some bulges on the side. This is a better picture than what he could see. It wasn't a perfect spherical shape anyway, when he looked through his telescope at Saturn. So we're getting rid of the idea that there's perfect circles up there, or perfect spheres. He looked at the moon with his telescope and found that it was pockmarked. All kinds of craters. Well, that's not perfect. Well, maybe on someone else's perfectometer it is, but on his perfectometer that represented imperfection. And then, not so smartly, he pointed his telescope at the sun and took a look at the sun and saw some sunspots on the surface. Again, these were imperfections on the surface of the sun. It's not a perfect thing up there. And so he was, with his observations, slowly destroying this worldview or perspective that scientists were bringing into their study of the heavens, that the heavens have to be perfect, with his observations. One of the other things that he observed was the phases of Venus. And it was known at the time that the heliocentric and the Earth-centered model of the solar system were being proposed, that you had these 2 planets, Mercury and Venus, that always stayed close to the sun in the sky. And so one way to explain that was in the Ptolemaic model to have those planets orbit inside the orbit of the sun. So the Earth's at the center, and you've got Mercury and Venus orbiting inside the orbit of the sun, and they're always staying kind of close to the sun. So they're matching the sun's speed as they orbit the Earth. Well, when Galileo made these observations, he noticed that Venus has phases. These are not the phases of the moon that you're seeing here. Those are actual phases of Venus. And it goes through phases just like the moon goes through phases. You see crescents, you see full Venuses, you see half Venuses. And the Ptolemaic model is going to have a hard time explaining that, because when you look out in the sky in the Earth-centered model, you're always going to see a crescent shape, because the sun's outside the orbit of Venus, and when you're looking at Venus, you're looking at usually mostly the dark side of Venus. The other side is lit, because the opposite side from you is facing the sun. So you're only going to ever see crescent shapes in the Earth-centered model. So this was another nail in the coffin of the Earth-centered model of the solar system. And Galileo made this observation. This, I think, is what really convinced him that we need to move away from this Earth-centered model to a sun-centered model for the solar system. Some other observations were observations of Jupiter's moon. He saw some objects that were orbiting Jupiter instead of the Earth or the sun. And so that was further proof to him, anyway, that things don't always orbit Earth, anyway. There's things orbiting other things out there in the universe. And this is actually taken from his notes on the subject. So the model of the solar system developed over a long period of time, but each step of the way, people had their own worldview that they were bringing into play, and Galileo, when he stepped up to the problem, was bringing sort of the modern version of the scientific picture of things, that you got to build a model that's testable, and he was out to test all these models of the solar system. So the hard part is when you're going to do science, the hot buttons in that kind of conflict maybe with Scripture. The places where you run into some trouble are the 7 days of creation versus the scientific model of the universe. It's 13-point-something billion years old, according to our measurements of the universe right now. How how do you get those to agree with one another? And then this idea of human evolution. What do we do with all these evolution ideas in the scientific community? Those are the hottest places where the debates rage. And one thing that I always ask myself when I enter into those conversations is, what's the most important thing from a Christian perspective? And really, the most important thing is the gospel message. Whether the earth was created in 7 days or whether it's been 13 billion years, is that important to the gospel message? I'm not so sure that it is. So sometimes those lead to consequences about what you read in Scripture, and sometimes they don't. I'm not sure that young earth versus old earth leads to consequences for the gospel message. I'm not all that sure that it does. That's a very important argument to be having. So anyway, the picture of our solar system is still developing. Roger came in today and mentioned that he saw in the press, I haven't seen the article myself yet, but there might be a 9th planet out there. Again. So if you remember, Pluto was demoted to dwarf planet status, and that was a sad time for a lot of people. Again, that was all a classification problem from an astronomer's perspective. We like to classify things into categories, and Pluto just didn't fit all of the planetary characteristics that we had out there. But anyway, there's evidence that there might be a 9th planet out there, but again, the evidence that we have right now is based on a few observations and largely on a model that an astronomer has built on a computer. He developed a computer code to model orbits of planets in the solar system. And I'm sure it's a very good model that he's developed, but again, it's just a model. And I know from my own experience in dealing with this problem that once you get to more than 3 bodies interacting gravitationally, the computational problem gets really, 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 really hard. You're not even going to believe how hard it gets. It gets hard. So this computational model, it's probably a good model. There's probably things that need to be worked out on it, but there's observations that sort of support what his model has been seeing. So what you see in this picture is the orbits of a bunch of things in the solar system. So the solar system that we know about is this little blue circle right here in the middle, and you see the expanded view of it. We've got the inner planets, and then we've got this Kuiper belt of objects that Pluto's a part of. It's a bunch of objects left over from the formation of the solar system. And then outside that, we have more objects and this proposed 9th planet orbit. Well outside what we know to be, or what we understand to be, our solar system. These orbits are huge, the orbits that we're talking about. But one of the observations that was made that kind of led this other, Brown is his name, that led Brown to make these computational models was the fact that you've got these objects all orbiting, and you see they're elliptical orbits, like we saw with Kepler, but the far points of their orbits are all kind of pointing in the same direction. That was an observation that was made by astronomers with their telescopes. And so the question for them was, when we look up in the sky and see all these orbits kind of pointed in the same way, that doesn't just happen. The dynamics of the solar system are too complicated and too chaotic to have orbits line up like this just right, so that when we look out in the sky they happen to be aligned this way. The chances of that happening are very small. And so he started thinking, well, what can drive this? Well, maybe there's another massive planet out there, or maybe there's enough mass in the Kuiper belts. Some other mass out there is making these orbits line up this way and stay aligned. So not only were they arguing that these orbits, it's unusual for that to happen, but they're probably going to stay aligned as time goes on. And the only way to get that to happen is to have some mass out there that's shepherding into aligning their orbits that way. And he brought this idea down to Brown, who got excited about it and started making computational models and recognized from his models anyway that a good explanation for this is to have this massive ninth planet, which is about the size of Neptune in his model, out there in an orbit that's 20,000 years long. It takes 20,000 years to complete one circuit around the sun. And this is the mass that could be making these orbits line up like this. And as he was developing this model, he recognized that there were some other weird orbits that were generated. And you can't really see it on this picture, but it's these two orbits that we're talking about. Those two orbits, so most of the planets in this picture here in the solar system, they kind of lie in a plane like the surface of this table. And most orbits of the Kuiper Belt objects also lie roughly in that same plane. The thing about these orbits is that they were tilted at about 30 degrees with respect to that plane. So the plane of these orbits, they're angled like that or like that. But the really funny thing about these orbits is that they're actually they lie in a plane that's perpendicular to the plane of the solar system. And that's weird, because our basic idea of solar system formation kind of almost requires that things form in a disk of material around the sun, the way that we understand the physics of solar system formation. So having orbits that are perpendicular to that disk are weird. And this model, having this huge mass out here, predicts that there's going to be some stuff orbiting in these perpendicular orbits relative to the plane of the solar system. And when he found that, he brought it to his observer friend, who's a Russian guy named Batchin. I think that's how you pronounce it. Who said, hey, I know some objects out there that actually do orbit in a perpendicular orientation. And so the two guys working together kind of pieced this model together and are proposing that there is a ninth planet out there based on the computer simulations and based on the observations of the astronomical community. And so in the near future anyway, we're going to be starting to point our telescopes sort of in this direction here to look for this ninth planet. Right now it happens to be at its farthest distance from the sun, so it's going to be pretty hard to see. We need some pretty powerful telescopes to take a look for it. But the fact that it's way out here also might explain why we haven't seen it before, because it's a 20,000 year orbit. It's going to take roughly 10,000 years to get from here all the way over to here. We haven't been around that long looking up at the skies with our telescopes. So it's interesting. The story of the solar system continues to develop. It's never a good idea to say that we know everything that's out there in our solar system. There's lots of stuff that we haven't seen yet, and we keep discovering more. So thinking about solar systems, that also brings the question up, is there life elsewhere out there in the universe? And I came across this story at the same time that I came across the story about Planet 9. So for about 40 plus years or so, we've had this SETI program in place, this Search for Extraterrestrial Intelligence. And in the last, 10, 15 years or so, we've had very dedicated missions to search for life out there in the universe. Not intelligent life, but microbial life even. So we've gone to Mars with these missions and dug in the dirt and looked for evidence of microbial life out there. And what we're finding is that the universe is a pretty hostile environment to life. So a lot of the scientific community looked out into space and thought, that's. So I guess the statement I'm thinking of comes from Carl Sagan, who wrote that book Contact. One of the characters in there looked out into space and he was having a conversation with his daughter about it. And, she was asking, "Do you think there's life out there, Dad?" And he says, "Well, it would be an awful waste of space if there wasn't." And that's sort of been the worldview that the scientific community has taken about the universe out there. And so we started all these searches for looking for life out there and finding that the universe is hostile to life. And so now the community is starting to maybe change that perspective and say, well, it's still an awful waste of space, and there still could have been life out there, but these habitable planets that we're finding, or these possibly habitable planets that we're finding out there, they weren't stable for long enough for intelligent life to develop. So that's the new model that's being proposed, that these environments just weren't stable enough to have intelligent life develop like here on Earth. They're starting to recognize at least that Earth is a pretty special place in the universe. The fact that we have intelligent life to ask these sorts of questions is pretty impressive. So one other thing about this story is that Enrico Fermi, who was a famous physicist, and he also had a hand in developing the nuclear reactor. He was asked once about aliens and life elsewhere in the universe, and he said, "Well, I've never met one, so I don't think they're out there." So there's all kinds of perspectives on this in the scientific community. I don't know what to think about it myself. I've gone back and forth on this question. I try to approach these types of questions with some humility, because I know that there's things that I'm not always going to understand. I don't know, when I look in the scriptures, I feel like I understand that Earth is a pretty special place, and that God had a special interest in putting us here on this planet. And that I get a sense that if there's no life out there in the universe, it doesn't mean that it's a waste of space. You read all those passages about the heavens declaring the glory of God. And so it's just because there's no life doesn't mean it's a waste of space. It's still crying out the glory of God. But I don't know. I don't know. My feeling is that we're not going to find life out there. Just because I know how hostile the universe is to life. The universe does everything it can to kill life and not preserve it. So, anyway, any questions about any of the stuff that I've presented today? We got a little bit of time yet. It's a lot of information.
What's the plane of the new planet, supposedly new planet, in relation to?
The plane of the new planet is proposed to be in roughly the plane of the solar system still.
Okay.
Yeah.
So what I mentioned earlier about the sphere of the Earth, that the Earth is a sphere, it must have been in that period of time in the 1300s or 1400s when they came to realize that the Earth was not flat. And Galileo was already knowledgeable about that, correct?
Yes, he was. Yeah. There was pieces of evidence that were suggesting that the Earth was not flat. I think, in fact, that model. We hear records. We see more records of people saying the Earth is flat than people saying the Earth is a sphere. I think that both of those models were in play for a long time, side by side, and there was evidence for Galileo anyway that the Earth was not flat. When he looked out at ships going out to sea he'd see the mass drop down over the horizon, and that said to him the Earth is not flat because the mass is dropping over the horizon. And there were other pieces of evidence too. People were starting to travel around the world a little bit, and so Aristarchus actually traveled around the world and looked at shadows to convince himself that the Earth was a sphere. So I think both the models were in play. People were still trying to figure out which was the better model. And then when Columbus sailed around the Earth, well, it was Magellan, I guess, that first sailed all the way around. That kind of convinced people, okay, we can travel on the surface of the planet and get back to where we started. It must be a sphere.
So if they accept that new planet, that cancels out Pluto?
Well, it won't cancel out Pluto, but it will be a 9th planet in our solar system again. We'll have 9 planets again instead of just 8.
Geoff, do they have a name for that planet?
They don't have a name for it yet because it hasn't been observed yet. They won't name it until they have good observations indicating that it's actually there. They'll just call it Planet X or Planet 9.
So if it takes that long to go around the sun, and it's at the most distant, they won't see it in our lifetime.
Well, our most powerful telescopes can see it out there. We just have to look very carefully for it, because space is a big place to look. They could observe it in our lifetime yet. It won't be observable with just your sort of average backyard telescope, though. You need the high-power ones to see it.
Geoff, where are the higher power telescopes in the world today? Does the United States have some?
There's the Keck Observatory in Hawaii, Mount Wilson in New Mexico. Or there's a couple there's one in Arizona and one in New Mexico that are pretty high power. There's the binocular telescope, which is actually 2 telescopes. I think that's in Chile, not in South America. But yeah, the U.S. has a couple, and the rest of the world has a couple.
University of Texas is a big astrophysical university, isn't it?
Yeah, I think so. Yeah.
They have a big system of telescopes, I believe.
Yeah, yeah. I'm not so familiar with that university. I know University of Arizona has some pretty high-powered stuff too. And New Mexico has the radio dish array, the very large radio array, but that's not going to help us find this planet. The telescopes that might help us the best are the ones that look at the infrared region of the spectrum. Just stuff that I'm going to talk about next time, actually. How do we know what we think we know about the universe? The infrared spectrum kind of looks at heat signatures, and so the telescopes that look at that part of the spectrum may have an easier time finding this planet, because it'll be warmer than the surrounding space.
Is that Hubble telescope still in operation? Is that usable for that or not?
Hubble is still in operation. It depends if there's a window of opportunity for them to observe or not. Because I'm sure that it's scheduled out to so many years in the future by other programs. You write proposals to get time on a telescope, and the schedule of the telescope fills up pretty quickly. I don't know. It may be that they can edge some observation teams out to look specifically for this planet. Sometimes they do that. The other thing about this Planet X that is interesting, at least from a model perspective, is we have this idea that there was a period of history where we had lots of asteroid impacts early on in the Earth's lifetime, and of course, one of the ideas is that that's what brought life to the surface of the Earth. We had a nice big cometary impact, and that comet had microbial life on it, and that's what. But there is evidence that there is that kind of bombardment in the inner solar system, that we had this huge amount of rocks and asteroids just hitting all the inner planets of the solar system. I mean, today we're pretty clean from that, but the idea was that planet X could have a role in taking and dragging stuff from the Kuiper Belt into an orbit that would bring it into an intersection with the inner planets. So it's gravitational interaction with Kuiper Belt objects throws stuff towards the inner solar system, so to speak. So maybe in 10,000 years we'll have another rain of rocks on us. Who knows? Any other questions? All right. Next time we'll talk a little bit about how we think we know what we know about the universe.
Thank you.